Now the topic is lazy evaluation in Haskell, and let's first start with an example. My range is a function which takes two parameters, start and step, and after seeing the right hand side, the body of this function, we see that this is recursive, and also we see the function returns one list which starts with start, and then that is concatenated with this recursive part, which is another list. And here my range is again called, and only thing which has changed in that recursive call is the starting position, right? So I think it is easy to see that this function, when we run say on input 1 and 1, so that means it starts from 1 and every step is 1, then we'll get an infinite list starting with 1, then 2, then 3, and so on. So if we think how that happens, first call my range 1 1 will return 1 here, then concatenated with my range 2 1, and then my range 2 1 evaluates to another item in the list which is 2, and then again my range call, and this time the start position is 3, and so on. So it keeps on going and we get an infinite list. If you just type this function in Haskell console and then run my range 1 1, you will see that you are getting an infinite list on your console, and that will never stop, right? So it shows Haskell allows us to define infinite sequence. Now to make meaningful work out of an infinite sequence, we can think of this example. Take 5 from my range 0 5. So here this my range 0 5, which virtually gives us an infinite sequence starting with 0 and every step is 5, so 0 5 10 15 and so on, and so that infinite list is virtually there, and we are taking only the first 5 items from that infinite list to do meaningful work, which is this one 0 5 10 15 and 20. Okay, now if you are interested to know what happens under the hood, how Haskell can work with this virtual infinite list, then we have to understand how exactly this take function works. That will make us understand this basic notion of lazy expression. So first let's define this repeat function, which is similar to that my range thing in the previous slide. So repeat function takes one parameter x and repeats that parameter again and again, and that gives us a virtual infinite list. So the type of repeat function is one item a is the input and list is the output. Now the body of the take function is here, and the type of take is first parameter is an integer, then second parameter is this infinite list, and third parameter is the output is also a list. Now let's see the body of take function, and we see that there are two parameters. The first parameter is an integer n, and when n is not positive, that means n is either negative or 0, which we write with the guard syntax, then this function returns an empty list, and it doesn't matter what is the second parameter. And that makes sense, right? Because if we are talking about taking 0 item or negative number of items from a list, that doesn't mean anything, so we should return empty list as the output. Now when the second parameter is an empty list, then it doesn't matter how many items we want to take from that list, the output should be always empty. And otherwise, when there is a positive number in the first parameter and we are trying to take that many numbers from this list, which is having a head x and tail xs, then what should happen, that head should come out, and then we have a recursive call, and this time our goal is to get n-1 items from the tail, because we already got one item from the list. So to take n item from the list, already one is done, so n-1 more item we need to take from the tail. That is how we can interpret this recursive call, right? So hopefully that makes sense how the body of take is meaningful. Now let's take this example in details and see under the hood what operations happen one after another that eventually makes us work with this virtual infinite list, and still we are in good shape. So this is the call take 3 repeat 7, and this is the take function, the body. So remember one thing, in lazy processing, Haskell does not do anything unless it is forced to do that. That is the idea of lazy processing, and you will see that helps us. So here take 3 repeat 7, we need to match that with one of the cases. Now does the first case match? To understand whether the first case matches, we need to do this comparison, right? So we do this comparison and we see that is false, so we understand that we have to now check with the case 2. Now to check with case 2, we need to understand whether the second parameter of the take function is empty or not, because that is what the body says, right? Case number 2. Now to know whether it's empty or not, Haskell needs to evaluate what is repeat 7, at least one step, right? So that's why Haskell now expands repeat 7 one step. It's forced to do that now, and that means we have 7 colon repeat 7 here. And now Haskell understand that this cannot be an empty list because at least 7 is there. So Haskell understand that the third case matches with this given input. And now let's apply the third case. So x is 7, so 7 is out, and then take 3 minus 1 repeat 7, correct? So 7 is out, take 3 minus 1 repeat 7, and mind that even this operation 3 minus 1 will not complete unless Haskell is forced to do that. That is the idea of lazy processing. Now we here again have a take call, right? So again we are trying to match which case of take is applicable, and that means we first need to understand what is n. This is 3 minus 1, so that computation has to happen now, otherwise we cannot infer whether case 1 matches. So that's why this operation happens and it becomes 2, and we are here, and 2 is not less than is equal to 0. That's why we come here, and that means repeat 7 has to be again expanded, and that happens. And now you see there is a pattern. We have to just repeat that, and that means this 7 comes here, and then this becomes take 2 minus 1 repeat 7, right? Now again 2 minus 1, that will be evaluated, that becomes take 1, and to match the case here, this has to be again evaluated, so that is expanded to this. So again now this matches with this part, so another 7 is out, 1 minus 1, and so on. This is 0, and when take the first parameter is 0, then this matches with this case, and we now know whatever is here, we don't need to evaluate that, because take 0, whatever is there returns empty list. So take 0, whatever is there, we don't care, and we can now return an empty list. So this is the crux of how Haskell manages this infinite list, because at some point we can ignore the remaining part of the infinite list, you see here, and then the whole thing can be replaced with infinite list, and we have the answer 7 concatenated with 7 concatenated with 7. That is the result of this call, right? Okay, now if we apply similar concept to compute Fibonacci series, we can design this function lazyfib with 2 parameter x, y. X comes out, then a recursive call on y and x plus y. Now we can do take 5 from this to make it simpler. We can also give a name fib to lazyfib11, this part, and then we can do take 5 from fib. Those are also allowed, and that gives valid first 5 numbers in Fibonacci series. And if you are interested to take only the nth number, then we can, or I should say, if you are interested to take the xth number in the Fibonacci series, your input is x, then that means we can drop the first x minus 1 item and take keep only the last one as your output. So in this example, this take 5 fib was returning this first 5. Now we want to take only the 5th one, so we are invoking fib nth 5th, and that will drop first 4 items, and then only the head of the remaining list, which has only 5, will be returned. So that means it will return 5, right? Okay, now another topic which is an hugely important one: how an user can define its own data type in Haskell. That's a very powerful feature of Haskell. Easily user, the programmer, can define his or her own data type to handle any arbitrary application in hand. Now to do that, we have to use the data keyword. First, a simple example. We know that in Haskell we have this two values, true and false. Those are bool types, true and false. Maybe let's first see that on console. GACI, and if I say x equal to true, and then if we want to know what is the type of x, and Haskell says it's bool, and that is by default. Haskell shows us that it is defined in Haskell. Now say for some reason the user wants to define another type boolean, and he wants true or false to be two options possible for this user defined data type boolean. Then Haskell allows that, and to enable printing of those type information, we have to add this line called deriving show. Show is adding printing capability. We are deriving that capability in our data type. So we do that, and after that, if I write x equal to true, same thing as before. And now if I check what is the data type of x, Haskell says it's boolean. So you see, boolean, there is nothing called boolean in the default Haskell library. The user has just defined its arbitrary name boolean and included true false in that boolean. There are two options in boolean, and Haskell started Haskell started recognizing that user defined data type for true false from this point, right? Okay, now let's do even more powerful thing. Say we are in a card game, and we need to define new data types related to card games. So first let's define what is suit. Then we need to write something like data suit, and what options are there in suit. It can be spades or it can be hearts. You know that these are two types of cards in a card game. There are more types, but to make it simpler, we are just talking about two types. And then this printing capability. And also in each suit there can be different ranks of cards, right? Like 10, jack, queen, king, ace. And let's define a type called rank, and these are the options possible for rank. Okay, and not only that, you can also define some alias, like card is an alias, and to do that we have to use this type keyword. So card is an alias for this tuple, and the tuple is of rank and suit. So these two things is a tuple, and card is an alias to that. Similarly, hand is an alias to this type, a list of cards. So one hand is nothing but list of cards, right? And one card is nothing but one rank and one suit. That is the main idea. Okay, now these two things here, suit and rank, they are called type constructors. That is an Haskell terminology. And we already talked about alias. Correct. Okay, now let's define some meaningful functions in this card game context. Say one function name is value. The input of this function is rank, something like this, and output is one integer. And these are the possible input, and these are the corresponding output. It's self-intuitive. Now we can have another function card value whose input is card, and we know that card is nothing but rank and suit. And in this particular example, card value function doesn't care about the suit. It just checks what is the value of this rank, and that is the card value. Okay, so now to show an example usage of this function card value jack comma hearts, so this is one card, right? Because there is a rank and there is a suit. Now what will be the value of this? It will be just same as the value of jack, and value of jack is 2, right? So this should just return true. 2. Okay. Will that help if we run this code? Maybe yes. So let's quickly run this code, and should not take much time. So these are the data defined type suit and rank, and then we have the alias card and the alias hand. Now what else we had here? We had these two functions. One is value function and one is card value. So let's copy the code value and let's clean it, and then card value, right? And then we can compile this, and now say if you just type for practice a card can be a rank and a suit, right? So if you give that, Haskell should recognize this as a card. That's powerful, right? And if you check the type of X, it says it is a card, right? And now if we define say a list of cards, say this is 10 spades, and then this is jack hearts, arbitrary, and we can have more. And if you say what is the type of Y, it says it's list of cards, correct? Okay,